Hello, this video is going to be a tutorial of how to run some categorical data analyses in R. The analyses I'll go over are chi-square tests, Fisher's exact test, logistic regression, and I'll also go over model selection using Bootstrap. So the dataset I'll be using is a popular dataset, contains information on patients with heart failure. And I've already loaded it into the global environment. It's from Kaggle.com. So let's take a quick look at the actual data set. So the criterion variable we'll be predicting is the binary event of death, whether the patient has passed away or not. All the other variables we can use are predictor variables, which contain information, demographic information like age and gender, as well as some measurements that were taken about the patient as well. So the first step is to start cleaning some of this information, because a lot of the binary variables were set as integers. Right now I'm just going to set them to as factors using as.factor. Next, because one of the variables, at least platelets, was pretty large, and I wanted to count it in units of 10,000, so this will make later interpretation a little easier. And also, I just wanted to show you how to center some variables by using the scale function and setting scale is equal to false. By scaling centering, is basically just subtracting by the mean for that specific field. So first things first, let's do a quick table. Let's just say we had only two variables, like high blood pressure, whether the patient had high blood pressure, yes or no, and whether the patient died. And let's look at that table. This will be rows. I should have named it, but the rows will be whatever the high blood pressure, and the columns is the death event. So using this table, you can get the chi-square test. You can run a chi-square test on it. And basically, the chi-square test is a test of independence. And the null hypothesis we're looking at is whether both variables in the table are independent. And that's basically what we're testing. And right here, after running the chi-square test using the chi-square.test function, it provides the chi-squared value, which is in this case 1.5, degrees of freedom, which is just 1, and the p-value, which indicating 0.2, which is a lot higher than 0.05, indicating that it's not significant. So we can basically conclude that we can confirm the null hypothesis that these two variables, high blood pressure and death event, are likely independent. So, but let's just say it was independent. One good thing to do is look at if it was significant. Basically, one cool thing to always have is the effect size. And right here is I created a function to calculate the effect size, and I'm going to use the formula for Cramer's V. There are a number of other effect size formulas you can use, or measures or metrics, but I'm just using Cramer's V because unlike the other ones like phi and odds ratio, they're specifically for 2x2 tables. And Cramer's V, even though in this case I showed it's a 2x2 table, but you can use Cramer's V for larger tables, larger than 2x2. So I set the function right here, and this is basically the formula. And to use this function, you just have to enter, Cramer's V is the name of the function. You just have to enter the chi-square value that you received, the total of the sample size, or the total of all the cells together, and degrees of freedom. These two, the chi-square and degrees of freedom, was going to be provided by the output, And the sample size, the n is just basically the sample size. So I can run it, and you can see it's 0.07, indicating for Cramer's V, anything like below 0.3, I would say, is suggested to be very small, like between 0.1 and less than 0.3. It should be at least 0.3 for it to have like a medium effect size. And oftentimes you might get requests where sometimes people just want to know if something's significant or not. You don't necessarily, they have two variables in mind, or that's all the information you have. And this is pretty good, especially, well, only if both variables are categorical. You can run a chi-square test and report whether it's significant, and also report the effect size, because it can be significant, but the effect size is pretty small as well. But if it's a little higher, it's even better. And this is like the simplest test you can do, and sometimes it's pretty much what most people would just want to hear. But yeah. But moving on, sometimes there are assumptions to a chi-square test, and sometimes it might be violated. And one of the assumptions is that the expected counts are less than 80% of the cells. The assumption for expected counts requires 80% of the cells to have at least an expected count of greater than 5. I don't know why it took me so long to say that, but that's what's one of the assumptions that are required. It gives you, when you run the chi-square test in R, it'll give you a warning on whether this assumption was violated or not. You can also check the expected counts by just doing the $ expected and for whatever you named that value as well. And as you can see here, it wasn't. But let's just say it was violated. There's an additional function you can add, which is simulate.p.value. When you're running the chi-square test, you just add comma, then this value, set it equal to true, and it runs a Monte Carlo simulation. So basically test whether, even if you violated the assumption, to still run a simulation to test whether you have a significant value or not. Another option you can also use if you have a 2x2 table is the Fisher's exact test. And you can use Fisher's.test, and let's run it really quick. Yeah, and it's generally more preferred for smaller data sets. And what it's basically looking at right here is the alternative hypothesis it's testing is whether the odds ratio is not equal to 1, meaning that the null hypothesis is that it is equal to 1. So if 1 is within this confidence interval, as you can see, which it is, so you can't necessarily reject the null hypothesis. The odds ratio right here is 1.4, and the p-value is indicating it's not significant. So this is me testing the same table, high blood pressure by death as well. So we can see high blood pressure in itself is not dependent on, death does not depend on high blood pressure, so that's just for a 2x2 table. Now, if you have if your table is larger than 2x2, you can also set simulate.p.value to equal to true. So you can run these large tables, and you'll use a Monte Carlo simulation to run it and test whether it's there or not, or whether it's significant or not. But if you do have a larger table, you might want to consider to try reducing it, especially sometimes it really depends on your data, but sometimes you might be able to reduce it. Let's say it's 4 values, maybe you can decrease it into like this sort of low and high, turn into more binary dichotomous, but that's something you might just want to consider. All right, so let's jump into the actual logistic regression. So now, right here, and logistic regression is basically it's when you have the criterion variable, in this case death, is binary. and we have a number, and all the predictor variables can be continuous or categorical. And right now, to run this logistic regression model, and it's a very popular machine learning algorithm that's often used, and also a very popular data set. And to do so, I'm going to use the GLM function. The y variable, or the criterion variable we're using, is death event tilde right here, and dot. Dot means throw all the predictors in the data set that I have. And the data set, I'm naming it, the data set right here we're using is heart. And family is equal to binomial, which this is important to include because it indicates that this will be a logistic regression model. So let's quickly run it. So as you can see here, this is, so this is the formula. This is our distribution of residuals, and right here it will provide the list of coefficients, all of our predictors, the estimate of the coefficients, the standard error of those coefficients, the z-value, and the probability, and the last column asterisk indicates whether it's statistically significant at 0.05 at least, dot meaning it's marginally significant. And this is the saturated model because we threw everything into the model. So we just, and the reason why we just wanted just to look at it, and we can see here that some things are significant and some things are not. However, this isn't the most parsimonious model. We want it to include as many predictors as needed, and we know that it doesn't necessarily need all the predictors. So we might want to use some sort of model selection technique. And one popular model selection technique is stepwise regression. Now, the stepwise regression that we'll be using is a backwards stepwise regression. And what that means, it'll basically, it's in the mass, package mass. And what the backwards stepwise does, it starts with the saturated model first, and then in each step it will remove one variable, and until it reaches a model where all the variables are significant, and it selects which variable, or I should be consistent, use predictor, which predictor that it removes is the one that contributes the least in each step. And then at each step, it just removes one predictor. And finally, it compares each model, the AIC of each model, and selects the lowest. The AIC is a relative fit indicator, a lower value indicating an improved fit for the model based on the data being used. And so let's actually run this. It's step AIC. So it's the function is called stepAIC. I have to indicate the model. This is the saturated model that I ran. I named it mod 1. The direction is backwards. And the reason why I'm selecting backwards and not forward is backwards starts with the fully saturated model. Forward will start with the intercept only model. And it's been suggested that the backward approach is, well, at least the forward approach is better if you have, let's just say, more predictors than participants in your sample. In this case, it's not that big of an issue with us, even though we have a good size of a number of predictors. Well, we also have about 300 participants in our sample, so we're going to go with backward. But and a third option can also run both as well. But for now, let's just run backward. Oh, and I'm sorry, I didn't actually load the package from library. And now let's run it, and I'll name it mod step. And basically right here, it will tell us the model that it is suggesting. Based on the step AIC, this is the best model to use. These are the predictors: age, ejection, creatinine, sodium, and time. So these are basically this is basically the model that was developed using StepAIC. Now, StepAIC, in actuality, it's a lot of statisticians are really not big fans of StepAIC. It leads to inflated R-square. It also leads to this issue of overfitting, meaning that there's an issue of inconsistency in that I can fit this model onto a new sample coming in and it may not produce the same results, or I can run the StepAIC again and it'll give me different variables. That's why, like, a lot of times, most times it's most recommended to use some sort of cross-validation, popular one being test and trained, like taking a sample and 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 like just fitting the model and testing it out. Alternative to that is to use Bootstrap resampling. Now with the boot.stepAIC package is I will basically take a sample of the data set that the data set that I'm using, 299 participants, and I'll do this a set amount of times, and I'll run the StepAIC over and over again on each sample, and I'm sampling for replacement. And then what it's going to provide is a diagnostic on the consistency of the variables, because I know that some of the variables, it might be significant in one sample, it may not be significant in another sample. In fact, it could be so inconsistent that it can actually switch signs. It could be significant, positive significant in one sample and negative significant in the other, and sometimes it may not be selected at all. And this is like it really provides some information on what to best include in this model. And also, it actually provides another layer of information, because maybe you may not be interested in finding the best fitting model. Maybe you want to describe how predictive a variable or predictor in the model is, and this gives you a good sense of that. So let's run it. The function is boot.stepAIC. I just indicate the model name. This is the original saturated model. Then I will indicate the dataset name, and I will be running the resampling like 50 times. So let's run it. Oh, I keep forgetting to call it first library and then run it. And it's taking a bit of time to run. I've only set it to 50, so it looks like it went through. So let's see what I named it, mod_boot. So let's see what it says. Let me scroll up all the way to the top. So, all right, so it's basically telling me here for each variable in the saturated model, how often, the percentage of times the predictor was selected. And you can see here, age was selected 100% of the time. High blood pressure, on the other hand, was only selected 16% of the time, 16% of the 50 sample, the resampling that was done 50 times. Coefficient sign right over here in this section will show how many times the sign switched. And what you really don't want to see is, you don't want to see an even split. You want to see either positive completely, mostly, or negative. When you see something like an even split, almost an even split right here when it comes to smoking, yes or no, it meaning positive sign, meaning that it's more related, it increases the odds of death, but it does 57% of the time. But 42% of the time, it showed that it actually decreased. So this probably shows, yeah, this is actually pretty unintuitive, because you would expect smoking to be pretty consistently positive with death. But so it basically suggests some further examining right here. but it's a good sign. And the percentage of the time it was significant, again, you want to see, high percentages right here. And this is basically something that you should closely review. And people who have like the most content knowledge, like knowledge of prior research, using prior research on studies investigating heart disease, this will basically help to make informed decisions on the best models to include. But this also suggests what predictors you should include into. I'm sorry, I mean models earlier. It gives you another layer of information um, to better examine past research that was conducted. And it also, right here, it indicates the final model that you arrive at. And so let's move on quickly to actually running the suggested model, which was right here. And so right over here, mod 2, I'm naming the suggested model, and I'm including what was suggested from the Bootstrap. So these are all the predictors I'm including. And let's quickly run it. Okay, so finally here, these are the results of the model suggested. Now let's go over something really important, which is actually interpreting the coefficients, which is what I wanted to do. Save it to the end once we finally arrived at a model we can use. And right here, what I'm going to do is, these are the log odds. The estimates are in log odds in that you're interpreting it as log odds. Like, for example, age for every 1 year increase, it's the 0.04 is the log odds. But what I want, it's an odds ratio. So what I'm going to do is exponentiate all of these estimates. Then I'm going to do an additional step, because sometimes I like to interpret it as like a percent. So I'm going to minus 1 from this odds ratio and times by 100. And basically, let's look at it right here. And I'm going to interpret what these results mean. And basically, for every additional, like, let's interpret age right over here. What does the 4.3 mean? So for every additional year older, the odds of death increases by 4.3% while controlling for all the other predictors in the model. So, and the reason why I did is sometimes it's just it's much easier to interpret than the log odds, and sometimes looking at the percentage, it gives, a lay audience a better sense. Now, 4.3, that might sound small, but when interpreting, you also have to be mindful of the units you're using. This is a continuous variable, so 1 year increase may just be 4.3%. I'm sorry, 1 year older might just be a 4.3% increase, and I know it's increased because it's positive and not negative. If it was negative, you'd be interpreting it as decrease. Increase. But let's just say a patient is 10 years older, controlling for everything else. That's 10 times 4.3, meaning the odds of death increases 43%. So that's another thing too you have to be mindful of, is the actual unit being measured. And I don't actually have any more dichotomous. I notice I don't have any dichotomous variables. But with the dichotomous variable, let's say age was dichotomous, like I had old versus young, and let's say young was like the baseline and old was set to 1. So here I would interpret it as, and let's just say that it was the same value, 4.3, it'll be the odds of death increases 4.3%. The odds of death increases by 4.3% for people who are older compared to people who are younger, while controlling for all other predictors in the model. That's how I would interpret it. And let's also look at now we have a model that we settled on, we might want to fit it on new data. So I created a data set and I set the values, like I said, set them to around where the mean was for each of the each of the variables in the model. So I just created this data frame, like age is 61, ejection is 38, and so forth. So let's call it new data 1. Let's run it. And now let's fit the model that we developed, mod 2, onto new data 1, and set type is equal to response. And we're going to use the predict function. And this will provide us the percentage, the probability of death, which is, in this case, 0.22. Now, just adjusting it here, I'm going to take this another observation. This is a data frame, but I just want to look at just one participant at a time. You can obviously have a larger data set, and you can fit the model to a larger data set. But here it's going to be the same data, but the only things I'm changing is I'm increasing age to 95, and also time I'm decreasing to 4, because time was negative predictor, seemed to decrease the odds of death. So what I'm going to do in time and days, so let's run it, and now let's predict using same model onto the new data point, new data 2. Let's run. So I expect it to increase, and it did at 94% probability of death. So another thing, one quick thing that you should always look at when running logistic regression models is multicollinearity, or any regression models, multicollinearity. It's an assumption that you have, that you hope that the variables are not too correlated with one another. More specifically, they're not linearly dependent on one another. And the issue with multicollinearity is that they basically increase the standard errors and decrease the reliability of the coefficient estimates. So it's a big problem. And one way you can check it is by looking at the variance inflation factor. If you see a variance inflation factor of 5 among the variables, is something among the predictors, and it's something worth examining. And it's also called VIF, and to run this VIF analysis, it's in the package car. So let's open it, and let's run the function VIF on the model that we selected, mod 2, and we see that none of the predictors are 5. Now, multicollinearity is a problem, but however, sometimes it is acceptable to have some degree of multicollinearity. One example is like if you have interactions, meaning that you have interaction between 2 or more predictors, which was not even considered in this data set. Interaction meaning that, let's say, men who smoke, men who smoke was a significant predictor, or something we want to look at. To do that, we want to include men who smoke. We just multiply the gender variable we had, sex, with the smoke variable we had, and maybe it could be a significant factor. And it would take prior understanding of the knowledge, or of being a content expert in the field, to basically maybe make that judgment call. But you can also use a lot of you can fit these things one at a time. Look at interactions. It's going to be pretty exhaustive. However, there are some better analyses for looking at interactions, or looking through various types of interactions, one of them being classification trees. It's a pretty good approach. So, but that's one thing we didn't consider. And earlier I noticed that smoking was not included in this, and I just from my knowledge, I expect smoking to be included, but maybe smoking is a significant predictor of death, but only for, let's just say, people with high blood pressure, and that's an interaction that should be included, and that's one thing we didn't consider at all in this model that we can consider in future models. So I hope you liked this video. I went a little rambly towards the end, but let me know if you have any questions or any other future topics you want me to go over. Here are the references that I used. Thank you and take care.